So, I'm sorry, I'm not a singer. I'm just a quantum physicist. I would like to thank the organizer. This is really a very enjoyable and great conference, so thanks a lot. What I would like to tell you today is about our work on quantum simulations using quantum computers on the cloud. So for those of you who are maybe new to Israel, this is Israel. It's very small, as you have seen. We are basically here, not too far from Jerusalem. And this is Bar-Ilan University in the suburbs of Tel Aviv. It was established a few years ago. This is my group, my students. Some of them you have already presented the works here, so you may have met them. We deal with the dynamics of complex quantum systems. And we have been lucky to be funded by the Israeli Science Foundation as well as private companies that like what we do. And I would like to acknowledge useful collaborations with the Rigetti team, especially Matthew Rigor and his team, Maxime and Bram, as well as other academic collaborations. So I mean, we have spoken a lot about quantum computers, and I would like to give you my own perspective of, I would say, just a user of quantum computers on the cloud. And the question that you may ask yourself is, will this work for me? So essentially, you have an idea, you would like to implement a circuit, and you know that there are some quantum computers on the cloud, and you would like to know whether this will work or not. You want to give a project to a student, maybe write a paper. And so there have been a lot of concepts that are very useful, and my feeling is that at the end, one feels a little bit confused of whether this will work or not. I mean, you can try it, but it would be nice to know a priori. So that's why I thought about the thumb rule, and apologize for the experts in the audience that this thumb rule is really a little bit very simplistic, but I think it's useful. And so the idea is that you take all the errors and you sum them, and if you are smaller than 50%, fine. If not, don't even try it. So let me give you an example. So let's assume you want to realize a square circuit. So there are n qubits and the depth of n. So there are overall n squared 2-qubit gates and n measurements. And then the requirement is that this total error, which is just the sum of all the errors, is smaller than 50%. That's what you should check. So let me give you an example with some numbers. So of course it depends what are the errors. What's going on? I'm really not good with the microphone. Huh? Okay, so here are some examples. There is okay, let's try this one. Okay, so these are some examples. Typical examples, typical number for superconducting circuits, not the best one, say the IBM one. The publicly available one, there are 1% 2-qubit gate error and measurement error. So what is the maximal size of the circuit that you can realize? Wow, I cannot use that. Apologize. So what is the best that you would? What is the best number? This one, maybe it's better.
Yeah.
Can't hear. You can take it out.
If you take it out, it works. Okay. Yeah, it doesn't really work. Okay, put it on. 1. Okay, 1, 2, 3. Great. So what is the number? What is the maximum number that comes out of this calculation?
10.
No, how 10? I mean, you have 10 by 10 would be 100 2-qubit gates, which is times 1%. It's much more than 50%.
So order of magnitude.
Yeah, so it's 5 actually. It's 5. Yeah. So what if I take the quantinum hardware, which is much better, and have these typical error rates? Then you get 15. Yeah, 15 times 15 to 125. Okay. So what is really nice about the thumb rule is that actually it really predicts the quantum volume. So again, I'm not saying that this is the quantum volume. I'm just saying that by chance this comes out exactly the numbers that you would get from the quantum volume experiments. And then this maybe can help us answer the risk question, which was, when can you provide me a quantum volume of 100? And the answer is never. So you would need an error rate which is 0.002%, and I hope you agree that that's not achievable with the current hardware. Okay, so forget about quantum volumes of 100. Okay, so because we are just an academic group, and a poor one. So we can use the free available quantum hardware, so something of this type, which means that we can use up to 5, maybe 6 qubits. And what I would like to tell, and this is what we have done, I think quite successfully during the last few years, publishing several papers in which we discuss topology, non-local games, some long-range interactions, Bose-Einstein condensate, quantum state, I mean, all different types of interesting topics in physics. And what is nice about these projects is that in each of them there is some new, hopefully theoretical idea, and also some experiment. So I can show you something that comes out of the cloud that makes some sense and has some relation to what was predicted. So I think it's, well, we enjoyed it a lot. So of course today I don't have enough time to speak about everything, so I selected 3 topics, but I won't really have time for the third one, don't worry. By the way, feel free to ask questions. I will be on time even if you ask questions. So the first project is about non-local games with 6 qubits. So what is really a non-local game? Basically, a non-local game is like a band inequality with many qubits. That's the idea. In particular, we had in mind this triangle game that was proposed by Bravi, Gosset, and Koenig. It's called triangle because the qubits are in a triangular configuration. And the paper is unreadable. Daniel and Nyaka really did a nice work in extending this work and also explaining it to us. So we thank them. But what is the non-local game? So non-local game, in this case, it's a collaborative game. Okay, so we all play together and we try to obey some rules. And the game is built in a way, I will explain you a little bit how it is built, so that quantum players can win 100% probability, but classical players only with a 7 out of 8 probability. So how does that game work? So there are 3 players. That's the simplest implication. It's a triangular game, so you guess that. Each player has 2 qubits, and on each qubit, basically, they need to write either 0 or 1. So they need to give an output to this classical dealer, and they need to satisfy some rules. So in principle, it's easy, right? They can talk. At the beginning, they can decide a common strategy. The problem is that the rules change every time. So every time that they play the game, the rules are different, and they're actually established according to these coins that are tossed. And the problem is that each player knows the results only of its own coin. So there are 8 possibilities, but in fact, the player knows only the result of its coins, so they don't really know which rule they need to satisfy. So these are the 8 possibilities of the coins, and which give rise to 8 possible configurations, 8 possible rules. I don't want to discuss what the rules are, but I want to tell you that there is no way that you can satisfy all these rules together. That's impossible. And what you can do, which is the best, you can basically essentially write 0 everywhere, and you will satisfy all the rules except the first one. So the classical players, they have a simple strategy that allows them to win 7 out of 8. But the quantum players want to do more than that. How? Through entanglement. So what they do at the beginning, before they begin the game, they share a common quantum state. Actually, this is called the cluster state. It's a state that is very shallow. So you just need, 6 Hadamard and 6 2-qubit gates to prepare. And then, here comes the trick. What they do, they actually perform a measurement on the qubit, which depends on the result of the coin. And so then they can use the non-locality of quantum mechanics so that although they are not telling the other players what is the result of the coin, nevertheless, there will be some correlations between the measurement, right? That's the idea of the Bell pair, that the one measurement influences the results on the other qubits so that you haven't transferred any information, right? There is this information part. There is no information that goes through, but nevertheless, the correlations are built in this peculiar way, which is non-classical. And indeed, well, we also added some error mitigation. This was just the simplest error mitigation. There is, A-1 method. The only thing that we did was that we used, we didn't allow the players to trick. So we did an error mitigation on each player individually. Otherwise, this would break the rules of the game. But OK, as you will see, this is not, doesn't change a lot. OK, so what we implement, basically, we just implemented this on a quantum computer. So I'm now going to show you the results that were put on the archive, for different quantum computers. So there will be different bars. And this 7, 8 is here. So you want to be, I don't know, I don't like anymore the quantum advantage notation. I think it may be quantum violation. would be better, but you got the idea, sort of some quantum bell non-locality, whatever. So we did that. We tried different quantum computers, and actually none of them was able to cross the bar. But unfortunately, Meron had to graduate, so I said, okay, let's write it up. We said we tried, we explained how we did it, why not? And so we were actually lucky because, in fact, Brian saw this archive post and said, oh, but actually, you know what? You tried the H0, but we actually have a better quantum computer, which is not available yet on the cloud, which is the H1. And maybe we can run the same algorithm on the H1, which we did, and said, and we, of course, said, yes, we'd love that. And so actually the H1 had 97% probability. What I would like to say is that this is a nice benchmark. It's very simple to implement, and it does sort of reflect what you would get from the quantum volume. So let's say Honeywell knows that H1 was much better than H0, and IBM also knew that. And if you do look at quantum volume of Bob Lincoln, it's about the same of IonQ. So it's a simple test. There is no randomized, etc. But I think it gives you a hint of how the quantum computer is working. Okay. So the next question that we asked in the same paper, which now is a little bit theoretical, a little bit more interesting, was, okay, so I take the IonQ, didn't cross the triangle gain bar. Does it mean that I'm lost? So I build this cluster state. Does it mean there are no quantum correlations on the state? And in fact, so we want to build better bounds. So we want basically to lower the bar so that even IonQ or IBM will be able to cross the bar. And so how you do that? The way you do that is basically using the idea of these stabilizers. So as you all know, stabilizers are these local operators for which the cluster state is an eigenstate. And so it's very easy to actually build the functions out of these stabilizers. Say if you multiply to stabilizer or sum to stabilizer, you get a quantity in a quantum observable that is very easy to compute quantum mechanically because they are all eigenstate. The state is a common eigenstate of all the operators. And so, and in fact, these rules that I told you about, they were just built out of products of stabilizers. So that's why, they were built in a way that the quantum state will win, of course. So they were just products of stabilizers. But you can think of, let's say, what if I take the sum of the products of all the stabilizers, all possible sums of products. So there are 64 of them. But the question is, what is the classical probability? So because there are these minuses, when you so the classical, if you try to combine the classical, you get this sum of 64 terms, and you try to give a classical value to each of these variables, and it doesn't work. And in fact, one can show basically numerically. So you check all the possibilities, and you find that at most the classical game can win with a 20, can make 28 out of 64. So it's already below 50%. But there is even a nicer question, which is actually what is the optimal operator that I can have? What is the best quantum operator that I can build so that I will have the best quantum to classical ratio? And this question was asked by Cabello. And for the specific state that we have in hand, they found what is the sum. So it's some sum of products. And for that sum of products, the quantum would give you 55. So there are 55 terms. And the classical one, only 19. And by the way, it's still an open theoretical question. What is this 19? And what if I take 7 or 8 or 10? Then it just becomes, you don't even know numerically. You cannot do it numerically. So I think, this is just a very nice question. What is the best ratio that can be found? But anyway, this ratio is already good because 19 over 55 is a good, a good ratio. And indeed, when you run it on the quantum, on the IonQ, you will get 41, which is much larger than 19. So you basically lower the bar, and then you can win with them. Much better. You can make, you can pass the students that would otherwise fail. Okay, questions? No? Okay, so let's move to the second part. So in the second part, I would like to discuss some work in collaboration with the Rigetti team about noisy phase transition, crossing a noisy phase transition. So I would like to think about the need or the interesting theoretical question of adiabatically crossing a quantum phase transition. So, okay, this is usually annealing. Okay, this is a classical phase transition. So you think, you start with a very disordered state, and you lower the temperature, and you try to order your state, and, going towards a ferromagnetic state, but you don't really succeed. And the reason is in quantum mechanics is that there is a gap that closes. Okay, now you see the movie again from the beginning. So it starts very disordered, you try to cool it down. So here you do the same, but with a quantum parameter. So you start in the paramagnetic phase, and you slowly move toward the ferromagnetic phase, try to get a perfect ferromagnet. But there is a problem, is that by definition of a quantum phase transition, there is a gap that closes. So if there is a gap that closes, you cannot be adiabatic. So there is no exponential suppression of defects. There will be always some defects. Nevertheless, because it's a phase transition, so there are universal power laws, etc. So everything is a power law, and also the number of defects that you will create is some power, and this is called the Kibble-Zurich scaling. Okay, so there is a particular scaling of the number of defects depending on the velocity. So the slower you go, the less so v is the velocity. This is no, well, looks like the same. Anyway, d is the number of defects. So the slower you go, the less defects you have, but it doesn't go down exponentially, but as a power law. And this power law, by the way, has some relation to Grover's algorithm. So this is actually as the square root of v, it has some relation to Grover's algorithm. What we had done a few years ago to extend this to the case, so here I discussed the case where you go smoothly, adiabatically, but you can also think of trotterizing your Hamiltonian. And of course, because we are using quantum computers on the cloud, we need to trotterize it. And to trotterize it, we basically go from a continuous adiabatic evolution to a Fouquet evolution. So something that has blocks, discrete blocks one after the other. So it's just a Fouquet Hamiltonian. And we showed in this paper that this Kibble-Zurich scaling would work also in the case of Fouquet Hamiltonian. For the express, that has something to do with the fact that the Fouquet is related to the high frequency regime, but the Kibble-Zurich is the low frequency, this gap that closes. So, the two don't really talk to each other. Okay. So how you do that in a quantum computer? So we take the transverse field Ising model that you're all familiar with. We trotterize it with using this very simple scheme. And this specific model has a phase diagram, which I guess you have all seen. It has a paramagnetic and ferromagnetic phase. It has also two other phases, one in the time crystal. So, this Google time crystal is just, realizing this Hamiltonian and then writing a lot of PR. No, there was a question about localization, etc. But okay. There is also a topological phase. And we have written a couple of papers where we studied this phase, the topological properties of this phase, which is interesting. But for this work, I'm actually, I want to use the simplest phases, the paramagnetic to ferromagnetic phases. So I want to go, around this core. So I want to start here in the paramagnet, and I want to go here in the ferromagnet. Okay, so we want to study the noisy Fouquet Kibble-Zurich. Okay, so Kibble-Zurich, but Fouquet because it's discretized, and noisy because I don't know. That's what these guys build, noisy quantum computers. So in the Kibble-Zurich, I told you, the slower you go, the less defects you have. N is the number of steps that you do, and ideally you want to do as many steps as you want, so that you will really go slowly, and have very little. Very little excitations, very defects, so you get like a perfect ferromagnet. But there is a problem, which is the noise. And we have naively one could say, well, probably the number of defects would grow linear with the number of noise. This is just an ansatz, which works pretty nice. So then there is an optimum. If you go too slow, then you have a lot of noise defects from the noise. If you go too, so basically. Okay, this number of defects will be the sum of these two terms, and you can even think of some optimal velocity that you can go through. And by the way, and this was also discussed in some previous work, not for the Fouquet case though. Okay, so what I'm showing you here is in blue, it's what would be the ideal quantum computer. So the number of defects just goes down, and in reality. It begins to go down, but then when you go too slow, so this is slow, this is fast. When you go this is fast, this is slow. When you go too slow, then the number of defects will grow up, and so there is this minimum. And we also realized it on a quantum computer, so it's a little bit hard to see the scaling when you have 3 points, but there is a minimum, so we were happy. Because there was a minimum, meaning that yes, it's sort of at the beginning the number of defects goes down, and then it goes up again. Okay, and by the way, there was around the same time a paper by the D-Wave group, which realized basically the same protocol, but in a continuous way. And you also see in that case also this non-monotonous behavior. So they were mostly interested in the Kibel-Zurich scaling, right? This is the square root scaling, which is here on the left. But actually what we sort of easily explained that this is, I mean, they also knew that because of the noise, at some point you lose, instead of going down all the time, the noise will let you go up. There is this sort of minimum. Okay, so you can also think of this as a way to benchmark the quantum computer, right? How low can I get? How low can I get is essentially telling you how quantum you are, how small the noise is. Daniel is unhappy, but no? You're happy, okay. Okay, good. So I wanted to show also some preliminary results, because most of you have already seen the same slides a few times already. So some preliminary results. It's about a question that actually I've been interested in for already more than 10 years, which is the question of an effective terminal description. So what I told you is that I do this quench, this adiabatic crossing, and then I end up with a messy state. I wanted the perfect ferromagnet, but I get a mess. And the question is, how this mess look like? And in particular, can I think of this mess as like a thermal state? So there will be some excitation, some number of defects. Can I assign effective temperature? And actually, I would like to say that in this case, no. The answer is no. One cannot describe this situation as a thermal state. And to sort of see that, what I'm going to show you is the ratio between the variance and the mean. So you can always, if you know what is the average number of defects, you can say, okay, this is my temperature. But then the problem is, can you, with the same parameter, one parameter, can you also fit the fluctuations of the number of defects? And that's already a question which is non-trivial. I mean, you need to see. So let me first show you what is, so on the y-axis I have the variance over the mean, which turns out to be a unitless number. And on the x-axis, you have the annealing time. So again, this is very fast and this is very slow. And this is what is shown here. The different plots, this is just a theoretical, because it's a transverse field Ising model, you can compute everything analytically. Well, at the end there is an integral you need to do, so there is some numerics, but it's just a linear numerics, okay? It's not the quantum numerics. So what I'm showing you here is, again, the ratio between the variance and the mean is a function of the system size. And you really see that there are three regions. There are like three plateaus. One plateau on the left, so this is the sudden quench. Okay, so if you do a sudden quench, essentially you're not doing anything. So just probing the initial state. Then there is the Kibel-Zurich scaling. Actually, this is the Kibel-Zurich regime. And you see that with increasing system size, it becomes more and more plateau. If you gave me an infinite system, then the plateau would last forever. But at some point, you will feel finite size effects. Okay, so this is what I really like about this plot is that actually these straight lines are numbers that one can compute. So this is 1/2. This is 1/2. This is 2 divided by 2 minus square root of 2. And see the paper by D-Wave for the references where this is not in your result. And this is 2. So it's a little bit, it's not really a critical exponent, but it's really a nice way to, you have the full distribution of the defects, and now you have a number, the ratio between the variance and the mean, which is sort of a fixed number, a universal number that tells you where, what are the properties of this distribution. So you can, if you see that the ratio is, well, this is a sudden quench, so it's sort of easy to see. The Kibel-Zurich and the finite size, they are both situations which have very little number of defects. So most probably you see very little defects, but still, the two are very well separated. You can recognize them. So what we would like to do now is to come back to the experiment. Oh, I haven't told you about the thermal state case. What would be in the thermal case? It turns out, and these are these plots here, so it turns out that if you do it sudden, okay, of course it doesn't. If you do sudden, then it works. If you do it very, very slow, it also works. They also, this is also 0.5 and this is also 2. But in the middle, this Kibel-Zurich regime will really lead to another plateau. So there is really another universal number that characterizes the thermal distribution. So what we would like to propose is that this number is actually a very good way to characterize whether what I'm seeing is a distribution of defects that is due to the Kibel-Zurich or to the thermal. So not only one can look at the scaling, which is one way. Here you could even, you just give him one annealing time, and I check my distribution, I can tell you, oh, this is a quantum distribution, or this is a thermal or classical distribution. So I really like this project. We haven't been, we know this is 1. I mean, this is about 1, but we haven't really, 3 minutes. Okay, great. I'm sorry, I don't have time for the third part. this is already question time, so I have a question. And so my question is, do NISQ devices have potential applications in machine learning and combinatorial optimization in particular? So do NISQ devices have potential applications in combinatorial optimizations? And my answer is yes, if you fund my startup. So we together with some friends from the industry, we are looking into optimization problem, combinatorial optimization problem. You know, the true problem that really people care about. Turns out it's not the Ising model. Okay, this is a spoiler. And we are trying to see how we can collaborate with them to make value out of a potential quantum computer. So in particular, we are looking into combinatorial optimization as heuristic solvers of the Ising model. Maybe even the simulators that have been developed or different quantum-inspired algorithms, which all eventually resort to an Ising model that people in the industry don't care about. So we are trying to bridge that gap between the money and the Ising model. Okay. Oh yes. So last slide. Last slide. It's AI is important. You should always have AI in your slides. So this is a smart archive. Personalized selection of daily preprints using AI. I highly recommend it. It will take all the preprints per day, and it will tell you, it will send to you the best preprints personalized for you, and it's for free. You should really try it. And with that, I would like to thank you for listening.